You can put any genes out there. Right? The upstream promoter here, they don't have to be the arabinose and ATC-inducible promoter. You can switch it to other kind of promoter if you want without changing the mechanism in the middle here. So you have some kind of modularity in the system. And the second thing is that you notice the name of the enzyme that I use here is kind of strange name, right? Probably unfamiliar to most of you. So we particularly use a specific class of integrase kinase. It comes from the serine recombinase family. And the strength of this system is that it can operate without the requirement of a specific factor from the host cell. So we don't use some of these enzymes in gene therapy, for example, because it can work in a mammalian cell, for example. So even though here we really show that it's working in E. coli, it's likely that these particular mechanisms can also work in some other cell too. Right? So these are the two strengths that I applied now. Now, okay, we get one which is working for one particular type of enzyme, right? Then one obvious thing that we are working on right now for sure is actually try to generalize the process and working on other class of integrase kinase to see that you can build other bits that may be able to operate orthogonally with that bit. Okay? That's the thing that's going on for sure. But maybe there's also other way that we can scale up the storage device given the limited set of recombinase that we have already. So this is a next topic that I can talk about. If you recall, the binary latch, I just showed you a few slides ago. You have a side, the B and the P side, and you have two output, right? You flip it, and you go to gather state. So in this case, you have used one set of recombinase. You can go between the two different states. Right? Now let's imagine if you have more side, more repetitive side. For example, here I show another design in which I have two repetitive P sides here and have three different outputs. Right? So what happens is that when I express integrase, I can either recombine these two sides or these two further sides. So I can go up to three different states here. Right? So here, with the new architecture, we can use one recombinase to reach up to three different states. So going one more step forward. And we actually show that at least it works for the DXB1, the same enzyme that we showed in the auto-rewritable memory switch. So basically here is also the cytometry result. In the original state, here it's supposed to express only CFP. And so when you look at the fact result here, the red and the yellow channel, you don't see any high signal. Right? But when you express the integrase, you flip it, and you see the two split populations. One population with the high IFP, and the population with the high YFP. So here we show that we can access all these three different states. Right, using that simple enzyme. But you can see that there's something is missing. Right. So here, there are three possible states. Yes, but you don't have an ability to choose to go to this state or this state. Right. So in the population level, all you can do is to go between the blue one and the mixed red and yellow. Right. So because of that, we try to figure out a way that we can control whether we can go from here to here or here. Now, here's the idea. So we have two recombination sites here that are the same. What if we can have some protein or some kind of repressor or whatever that can bind next to this recombination site and temporarily block it whenever we want, right? If this works, then we can have an ability to choose to go to one state or the other state. For example, in this case, we can try to block the switching to the yellow state. Right? And that's the idea. And so we have some preliminary results that show that this thing might work here. So here we put the TET repressor binding site next to the P site, right? And we show here that this is before switching, so you're in the CFP state, so you don't see any red or yellow. Right? Now, when I induce it with arabinose, which induces the integrase expression, so what happens is that you get a split of the population, as you seen earlier. But in the case that you have 10 persons in the cell, especially in the cell, then you have lower probabilities, about like half, the case that you don't have the 10R. So somehow 10R, as we expected, it go near the side and reduce that chance of going to yellow state, right? And if we inactivate the 10R, right, for example, adding ATC to the system, then we bring this thing back to about 20% again. So I didn't show the other bar here, but we actually repeat it a few times and get a pretty consistent result here. So note that we haven't optimized this system yet, so it could be possible that we can push the difference here to be even more dramatic. Right. Now let's move on to the final topics today, which is the combinatorial data storage system. So if you recall from the earlier slide, when people built the counter that counter to fit, right? So those counter it work by flipping one bit to be one state, flipping the other bit to be the other state. So those counter function is model code counter. So basically the number of bits that flip is mapped to the different state. Alright. It's good, it works, but here the number of states you can reach is going to grow linearly with the number of bits that you have. Right? If you want to increase the number of states you access exponentially, then you want something like a combinatorial counter, right? That counters a base 2 number. So people have written about that, but the difficult part is that you need a bit that can go back and forth between 2 states, and you need an ability to connect them together, right? So that this thing can work together as a counter. Now, note that the ability to go back and forth between 2 states reliably, it has to be achieved, that we just showed on the other slide. It never worked a few months ago. Right, so if you zoom in on how this thing might work, right? You can imagine that the counter is a device. So you have input coming in on one side. You have some output whose output level to represent the number of the input pulse. So here's the count of the input number, and here's the input things. So if you look at it closely, the least significant bits here, it go back and forth between 2 states, 0 and 1, 0 and 1, every time the input pulse comes. Right? The next bit, you go also switching, but with half of the frequency of the previous one. And the next higher significant bit, you also go again, but with half of the frequency of the previous one. Right? So the basic device inside the counter that you need is basically some kind of device that allows you to cut down the frequency of the input that you receive by half. So here is the basic building block of each bit in the counter, which in electrical engineering they call it a toggle flip-flop. Right? So I have input coming in here, and it should toggle back and forth between 2 states using the same kind of input powers. Alright, and so we lay it out in terms of like, okay, if you have like this integrated CNS device working, so how it might work. And here's the structure that we come up with. So basically, you need 2 latches that connect together, right? Supposed to be able to operate orthogonally. The purple one and the blue one here. All right. You have the input, external input, which is supposed to be complementary to each other, the plus and the minus, controlling the 2 different integrators of these 2 latches. And you have the output complementary to each other that connect to one of the latches here. All right. So how is it supposed to work? So let's say you start from the state which is in the input minus state, output minus state here. Right. So you can see that you have this guy, it remains in the current state because you already have exogenous, but you don't have integrators. If you remember from other slide that I showed you earlier on, for this system to work, integrator is required for switching in either direction. Exogenous is the one that says which direction you're going to go to. All right. So here, you remain in the current state because you don't have integrators. But this guy, you have integrators alone, no exogenous. So it should drive you to the LR state. In this case, it's a plugging down, so it's already sticking the LR state here. All right. So you have input minus and output minus. So if I switch the input to input plus, so what can happen is that here, now you already have integrators coming out, you have exogenous coming out, right? And so you express this bit, and you have both integrators to switch it to the BP state. So this bit switch, but this bit, it no longer has integrators coming in, so it remains in the current state. So the state of the output doesn't change, right? Okay,